Okay, in this section we're actually going to go back to column vectors. And we already have talked about spans of column vectors. Let's see if we can find bases. So what that means is finding linearly independent sets of column vectors that have the same span as a given set of vectors. And this is going to seem like deja vu because we have done similar problems before. But it's always good to think about how you would do such problems. All right. So suppose we have a set of column vectors here, and we want to guarantee that this is a basis. Now, we don't know that these are linearly independent. All right. Now, what you can do is we know that row equivalent matrices have the same row space. So what we could do is we could transform these vectors into row vectors, row reduce, and take the rows of the simpler matrix as our new column vectors. Okay, so that's a good way to do this. We're going to take these column vectors, change them into row vectors, row reduce, and then take those simpler vectors back into column vectors. So that's exactly what's done here. These column vectors are changed into rows. Notice the first column here is the first row here. And so on. Second column here, second row. Go ahead and row reduce, and we know that row reducing does not change the row space. Okay, after you row reduce, you get these vectors. We can take out these two non-zero vectors here. Here we have two non-trivial row vectors. Now we turn those into column vectors, and we know that these two vectors span the same space as these four vectors here. So in fact, here we have a set, and we know also that these are linearly independent, so we now have a basis for our column space. Now, we can multiply these vectors by any constant without changing the span, and that will make it look nicer. So if I multiply this one by 11 and this one by 11, I get some nicer looking vectors. All right, so let's look at this example now. And this example really is very much the same as the previous example. We have a set of column vectors. We want to find a basis for the set of vectors spanned by these vectors. We do the very same thing. We write these as, we change these column vectors into row vectors. We row reduce. Now we have three vectors. The three rows are three vectors that span the same space. We write them as column vectors, and that gives us a basis for the set R. Okay, now in this section we relate the notion of basis to the notion of non-singular matrix. And if you remember, we had this long list of equivalence things to non-singular. And we're going to add another condition, which is that the columns of a non-singular square matrix form a basis for that particular vector space. So a lot of things that we can get from the fact that a square matrix is non-singular. All right, now, so how are we going to prove this? So we want to show the columns of A are a basis of CM if and only if A is non-singular. So first let's prove the forward implication. First, suppose that the columns are a basis. If the columns are a basis, that means that they must be linearly independent. Okay? If we have linearly independent columns, then we know if A is a square matrix, then A is non-singular. On the other hand, suppose A is non-singular. Then we know that the columns are linearly independent. And we know that for a non-singular matrix, also we know that the column space spans the entire vector space. So that means the columns of A are a spanning set, and they're also linearly independent, so they form a basis. Okay. So here's an example of a 5 by 5 matrix. Turns out that this matrix is non-singular, so that means the columns here form a basis for C5. And as I mentioned, we now have a new condition that we can add to all the other conditions that are equivalent to non-singular. So that's a short section, but very useful.